very excited to introduce our speaker today. He is a NASA and JPL Solar System Ambassador, and Ron is an outreach speaker for the Raleigh Astronomy Club as well, and a volunteer educator and exhibitor for the North Carolina Museum of Natural Sciences. And he's a science instructor and volunteer for the Ollie Lifelong Learning Program at NC State University. All right. And Ron, if you want to start sharing your slides.
Okay.
I'm passing it off to you.
Okay, here we go. And share sound. Okay. Can you hear me well?
Yes, we can hear you and we can see your presentation. Okay.
So the before I start, I am not an ambassador.
Oh,
I
I'm
wish
so
I
sorry.
Was, but
so sorry. Raleigh Astronomy Club then.
Yes.
Thank you for correcting that.
Yeah, okay. So our topic today is Jupiter, the planetary wrecking ball, and it's about the migration of Jupiter in the early solar system. So this migration is covered in something known as the Grand Tack Hypothesis. And there was a cover article in May of 2016 about this Grand Tack. And also just last year on the NOVA program, there was a series called The Planets, and one of them was about Jupiter. And that was a wonderful program. If you ever get a chance to go back and look at it, I would highly recommend it. And as Sam said, I'll answer some of the questions at the end. Hopefully. So now, Jupiter was the first planet to form 4.5 billion years ago, and it formed beyond the ice line in the solar system. And the presence of large amounts of gas, dust, and ice means it could have started forming sooner and become larger than the other planets. So here we have a graphic of our solar system. The distances are not to scale, but the sizes are. And you have the terrestrial planets closer to the sun here on the left. And then there's something called the ice line. And beyond the ice line, ice played an important part in the formation of the larger planets, the gas giants. So Jupiter and Saturn are known as gas giants. And then Uranus and Neptune are known as the ice giants. Jupiter and Saturn also have ice, but the proportion is not as high as Uranus and Neptune because they're out much farther out in the solar system. So in the 1990s, the nebular hypothesis of our solar system began to unravel. So what is the nebular hypothesis? Well, basically, it was that the planets in our solar system formed under the influence of gravity from gas, dust, and particles that were orbiting around the sun in a giant gas cloud. And the gas cloud was in the shape of a disk. And as I said, the planets formed from dust, gas, and ice. And interior to the ice line, gas and especially ice were much less plentiful due to the heat of the sun and the solar wind. The sun was much more powerful back then than it is today, and it really had an influence on those inner planets. So why was the nebular hypothesis being questioned? Well, there was updated research and observations of our own solar system. And then since the 1990s, there was observations of exoplanets and many other star systems, and also increasingly sophisticated results from computer simulations. And as they looked at those things, they noticed that there was anomalies which arose between the above research and the nebular hypotheses. So what were some of the questions that they were having arise there? The first one was, why isn't there a planet where the asteroid belt is located? And here's the asteroid belt. It's between Mars and Jupiter. And they were saying, there is some material there, but according to what we know about celestial mechanics, there should be some formation of a planet here. There should be more material and a planet. Then another question was, why is Mars so small compared to Earth and Venus? So here you see Venus and Earth, and then Mars is significantly smaller. And that was probably one of the top questions that they had. Why? They knew that Mercury was smaller because of some impact events and other factors, but Mars was the one that really piqued their interest. And then, of course, there's a lot of people ask this question, how did Earth acquire its water? And this is a really cool illustration here. This is, if you took all the surface water on Earth and rolled it up into a sphere, it would be about this size compared to the rest, to the planet Earth. And that's not a small amount. Most people think it would be larger because water covers 2/3 of the surface of the Earth. But the average depth of the oceans is about 3 miles. So that's not very thick at this scale that we're looking at right now. So it would form, the total water mass would be about that size. So another thing that was the exoplanets. When astronomers started looking at exoplanets, they were seeing things that they thought were kind of unusual. So the first exoplanets were confirmed in the 1990s, but many more were discovered after the launch of the Kepler and TESS space telescopes. And here's an image of the Kepler, which closed down operations in 2018. And here's TESS, which started in 2018. Now, where did they look for these exoplanets? Here's a graphic of our Milky Way. Here's the center of the Milky Way, up here, the bright spot. Here's our sun down at the convergence of all these lines. Kepler was looking for exoplanets in this yellow cone here. Now, a lot of people expected the TESS that would cover a lot more area, but it's not. It's covering a smaller area. It will discover more exoplanets than Kepler, but astronomers mostly want to know not how many more exoplanets are. They know about at least 5,000 exoplanets, but they want to know more about the exoplanets that they've already seen. They want to be able to create hypotheses about how our solar system formed. That's why it's in a smaller area. That's where they're going to concentrate. This is an illustration of the night sky around the entire planet Earth. And here you can see this is flattened out. The sphere around our Earth is flattened out here in this image. So you can see the Milky Way dips down here like a U-shape. And all the little dots you see in here are exoplanets that they've discovered. And there was quite a few. When Kepler came online, as I said, that was looking at a cone-shaped area in the sky, and that's what this blob is up here. That's where most of the planets that Kepler found were. Oh, and just to, in that prior graphic, it also said that there was about over 4,000 exoplanets formed by the year 2019. So this chart here is really neat. It's a graphic of all exoplanets that were formed through the year 2000 that we discovered through the year 2015. And the yellow ones are the ones that were discovered by Kepler, and most of the blue ones were discovered by ground telescopes. Now, the x-axis down here is exponential, and it shows the number of days that each of these planets orbit their star. So here you have 1 day, 10 days, 100 days, and 1,000. They're going up by factors of 10 here. And the y-axis is the size of the planet expressed as a comparison to Earth. So here, this first line across is the Earth's size, then Neptune up here, then Jupiter here. This is also on an exponential scale. And where this X is, that's approximately where Earth would fall here. So the astronomers were looking at this, and some of the questions that they had were, well, some of these dots on the chart are very unusual. And the first one that they looked at was up here, and they said, look at this. These are all Jupiter-sized planets up here, and they're orbiting. One thing I should add is that the orbital period roughly corresponds with the distance from the star. So when they looked here, they said these are all Jupiter-sized planets or bigger, and they're orbiting closer to the sun than we are. So how could that be? How could a planet as large as Jupiter and a gas giant form that close? If you look, some of them were like had orbital periods of only 3 days or less even. Very unusual. So here's an illustration of what they call the hot Jupiter. These planets in this yellow outline up here are often referred to as hot Jupiters. Then another anomaly that they saw was in this area here. And they said, well, these are kind of about the size of the Earth, or maybe up to twice the size of the Earth. But they're in farther, there's fairly many here. Why don't we see these planets, which they referred to as super Earths? Why don't we see them in our own solar system? And this is an illustration of what they were referring to. This is an exoplanet, an artist's interpretation versus Earth. You can see that the radius is probably about 2 times the size of the Earth, but there are no super Earths in our solar system. So questions that were developed because of these observations were, why aren't there any hot Jupiters in our solar system? And why aren't there any super Earths in our solar system? One early conclusion was that the gas giant planets could not form close to their star because of the radiation, the solar wind and the heat. They could not form close to the star, so they must have migrated there. This is another important photograph. It was made by the ALMA radio telescope in South America, high in the Andes. And here you see a planetary disk around the star that recently formed. And the star is in the middle, and the gas cloud around it, they detected these bands there. And these are gaps in which planets are forming. So that confirmed to them, a lot of their hypotheses about how these exosystems formed. So, so this is how they cleared their orbital pathways of the gas, dust, and ice. So those planets were accreting that material onto themselves to become larger. And this is a photo of the ALMA radio telescope. It's huge. If you ever are able to look it up, it's worthwhile. So now, after the exoplanets, there were computer simulations which astronomers are using more frequently. And some of these simulations require a lot of computing power, and much of it became available in the last 2 decades. So using input from what they're seeing in the exosystems, they're simulating how planetary migration could possibly have occurred. And they found that it was indeed a highly likely possibility. So what do they do to make these simulations? Astronomers construct a model of the early solar system and run simulations covering billions of years to see if their model results in something like what we see today. So this on the left is an early part of that simulation when the solar system was first forming, and then midway through to today, and then finally on the right, like we see today. So here's a video about those simulations. Sorry.
Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the Sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of the thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk. But the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbits, and many unlucky asteroids and comets and dwarf planets get kicked out of the solar system. The migrating giants wreak gravitational havoc. The distribution starts out quite flat, but as most small objects get tossed out, others settle into stable orbits that allow them to coexist safely with the planets.
So that was a pretty interesting video. And how are simulations used? Many of the beginning parameters of the simulated solar system can be varied significantly. So, for instance, they can vary the distance from the sun at which Jupiter formed. Of course, they have pretty good ideas, but they're not totally certain yet. Or such as the size and rotation of the original gas cloud which formed the solar system. So there are many, many of these parameters which they can move around. And thousands of simulations can then be run on many combinations of variables covering billions of years. So you can see why they would need such powerful computers. Even though tiny changes in the beginning stages of those simulations can have very different ultimate outcomes, the results tend to fall into complex patterns which are expressed as probabilities. Then the probabilities are matched against what we see in our own solar system and other solar systems to develop hypotheses. So for instance, they might say, well, according to the simulations that we ran, there's like a 25% chance that we should see super Earths in our own solar system, or 10% probability that we would see Earth forming at the size and orbit where it does today. And there's many other things that they check, like the asteroid belt and et cetera, et cetera. The next video I'm going to show is a clip from that NOVA series on Jupiter. And it's very good. I apologize, it's a little bit jerky in spots, but you'll get the idea. So to introduce it, after Jupiter formed, something unusual occurred. It began migrating inward towards the sun. Clip there, that was probably the core of what we were talking about during this session. So this migration of Jupiter and Saturn is known as the Grand Tack Hypothesis. So what is that? If you look at this graph here, you'll see an x-axis here, and that's showing distance from the sun. And it's measured in astronomical units, or AUs, of distance from the sun. 1 AU is the distance from Earth to the sun. So here, at this first hash mark, that's we can see where the inner rocky planets are. And then as we go out, you see this is where they believe that Jupiter formed at about 3.5 AUs and Saturn at about 4.5. Then they migrated inwards to about Jupiter to about 1.5, and then migrated outward to where Jupiter is today, which is about 5.5 astronomical units, and Saturn out to about 7. Now, also, when they moved back out, they kicked Uranus and Neptune out much farther into the solar system. But we're concerned here about this part of the graph right here. But that program left one big question unanswered. When I looked at it, I was saying, that was totally amazing, but, how could a planet as big as Jupiter and Saturn move into the inner solar system and then amazingly reverse course? I mean, here's the size of Jupiter compared to the Earth. You just don't, change the momentum of something like that using battery power. You need to get a lot of energy from someplace to change the direction. So it's all about the exchange of energy between Jupiter, Saturn, and surrounding giant clouds of gas in our solar system, that protoplanetary disk in which the planets form. So why is the Grand Tack a hypothesis rather than a theory? It's a hypothesis because, rather than a full-fledged theory such as relativity or quantum theory, because it cannot be tested or verified yet with updated observations. So now here's some of what it's all about. Here you see the orbit of Jupiter going around the sun. And as it's moving around, it clears the gas out of its path. And on the outer side, there's more dense gas here. And you can see how Jupiter is drawing some of that gas onto its surface here. And also, besides accreting it, it's also moving it away from itself. And then there's that interaction there has the effect of pushing on Jupiter. The exchange of energy pushes Jupiter inward. There's also a less dense gas inside of Jupiter's orbit, which is pushing outward, but it's less powerful in the inward push. So the net effect is that Jupiter moves inward towards the sun. Here's a simulation of what it might look like. And here you have the planet forming. You can see these arcs of gas joining with the inner gas cloud and with the outer gas cloud. And those represent the gas and the energy being exchanged between Jupiter and the gas clouds. So now, here's another illustration of what you just saw. So now, here the x-axis is the distance to the sun, and the y-axis is the density of the gas cloud. So here you have Jupiter, and there's no gas in its path along here. Then you have the gas cloud, which builds up over here on the inside, and another more dense gas cloud out here just beyond Jupiter's orbit. So what happens is here you see the outer cloud pushing inward and overcoming the outward push here. So Jupiter starts migrating inward. But Jupiter is not alone. Like it said in the video, Saturn is forming. It started forming shortly after Jupiter did. And it also was clearing out a pathway in its orbit out of that dust cloud. Now here's the inner cloud, and the outer cloud. The outer cloud is pushing harder than the inner cloud. And so now Saturn is going to start migrating inward. But being smaller and having an even bigger gas cloud outside of its orbit, Saturn moves faster and it winds up catching up to Jupiter. So now what happens is, As Saturn catches up to Jupiter, it clears out the gas between the two planets. So now you see that gas cloud is, down to a small size here. Now there's less dense gas on the outside of Jupiter than on the inside. And we just saw, according to the rules we just saw, the inner cloud now pushes harder pushes harder than this smaller cloud here on Jupiter. So this causes Jupiter to slow its inner migration. Now, there's other things going on here. One is that the orbital pathways of the two planets then start overlapping, and the planets lock into an orbital resonance that they were talking about in the video. So for every 3 orbits of Jupiter, Saturn orbits twice, and it's in a very regular pattern. So this means that the two planets start moving in tandem, which stabilizes their orbits from migrating any farther. So in other words, where Jupiter was then slowing its inner migration, now it stops. And here's an illustration of what happens in these resonances. So it's like a parent pushing a child on a swing, only let's say that they're planets. So when the child is moving back in the arc and the parent pushes it, just as the child reaches the very top of that arc, just a little push will give it a big motion in the other direction. But if the parent pushes the child when the child is still midway through that swinging backwards, that'll dissipate all that energy and the swing will stop pretty abruptly. The resonance also means that denser gas on the outside of the combined pathways can pass through to the inner side. So now these planets are maintaining their energy level, and what's happening is everything is being drawn naturally towards the sun, just because of the sun's gravity. But now the gas cloud is going to be drawn from beyond the two planets more towards the inside. So as the gas moves inward here, and as the gas passes through, energy is transferred from the gas to the planets. It's like flicking 2 coins. If you move this coin here, which is the gas, and it hits this other coin, which is Jupiter, the gas here as this first coin slows down and the second coin takes off. So that's what's happening when the gas is passing through from outside to inside the orbits. The two planets pick up the energy from the moving gas, and as the gas moves inward, the gas density on the exterior of the orbit decreases, and Jupiter and Saturn begin migrating outward. So you have the denser gas here and the less dense gas on the outside. So now going back to that chart, as Jupiter and Saturn gradually move outward, they fall out of resonance because their orbits are getting larger. And at the same time, the gas clouds around them continue to dissipate, and the two planets settle into their final stable orbits where we find them today. So they moved inward and then they moved outward. And they had a big effect on those inner planets, the 4 rocky inner planets. So how can the Grand Tack hypothesis answer these questions? Why isn't there a planet where the asteroid belt is located? Well, as it was shown in the video, when it went through the area where the asteroid belt is located, it threw around all the material, or most of that material that would have formed the planet, and it scattered it all over the lot, a lot of it going into the inner solar system. So there wasn't enough left to form a planet. Why is Mars so small compared to Earth and Venus? Same reason, only Jupiter stopped its inner migration close to where the orbit of Mars would ultimately form. So Mars had not yet formed. So Jupiter threw out a lot of the material that was going to be compressed into the planet Mars. How did the Earth acquire its water? Well, when Jupiter came in, it was coming in from the outer solar system where water was much more prevalent, and it had all these asteroids and comets around it that when it reversed its direction, it deposited a lot of them in the inner solar system. And those were later brought into the formation of the planet Earth. Why aren't there any super Earths in our solar system? That's because as Jupiter ended its inner migration, it threw all these asteroids and other material towards the sun. Those materials collided with any super Earths that probably were there and caused them to move and orbit spiral into the sun. And why aren't there any hot Jupiters in our solar system? Well, there were. Jupiter was in the inner solar system, but then because of Saturn, it migrated outward. So if the Grand Tack hypothesis is verified, it would explain why our solar system is so unlike the other stellar systems we have observed thus far. And in the next few years, the James Webb Telescope and other advanced enormous giant telescopes, ground telescopes, will come online and should help provide the evidence needed to verify the hypothesis. And so now, if you have any questions in the chat box, Sam, if you would like to read those.
Yes, we have a lot of questions coming in. So thank you all so much for submitting your questions. Okay, so there was a question early on about do we know where the disk came from for our solar system?
That is a very interesting question. And yes, the disk was formed from clouds of the original, that were left over from the original Big Bang, plus gas clouds that formed after the explosions of supernovae. And those supernovae provided the heavier elements that we now see in our solar system.
Right, wonderful. Lydia was wondering, so is there technically water on Jupiter, Saturn, etc., because there's ice on them?
Yeah, and there's not only water ice, there's many forms of ice, like methane, for instance. One of the moons of Saturn, for instance, Titan, there's much ice, and that ice almost makes, because it freezes at a much lower temperature, Titan appears to be almost like Earth, only using these other ices and gases to form something that looks like Earth, but in some ways, but very different than others.
Yeah, definitely. Wouldn't be as hospitable.
Oh, definitely not.
For us.
You better bring an overcoat.
Yes, definitely. Luke was wondering, is the ejection of material by gas giants how Sedna and other planetoids were formed?
Yes. Could you repeat that, please?
Is the ejection of material by gas giants how Sedna and other planetoids were formed?
It's very possible, yes. And it's possible that the migration of Jupiter and Saturn also caused other planets that were present in the early solar system to take off either into the way outer solar system, and make a possible planet 9 that they're hypothesizing now, not Pluto, but another planet 9, and for other planets to leave and go into interstellar space.
Right. And Cash was wondering, why does Saturn have such large rings and Jupiter have such small rings in comparison, if they're both gas giants?
I think it was probably because of the size of the moon. That, as I recall, Jupiter or Saturn's rings formed from the pulverizing of a moon that got too close. And it's just a matter of the placement of where those moons were.
All right, great. And Rexon was wondering, what if Jupiter were bigger? What would have happened to Mars, and would there be life on Earth?
Probably Mars would not have formed at all, and Earth, it would not be here. Maybe Saturn could not have exerted the force that it did on it and could not have kept Jupiter from coming in farther.
Yeah.
That's my guess of what would have happened.
Yeah, we don't know for sure, but yeah. I would agree with you there. I'm not sure if Saturn would be able to pull Jupiter back in time if it were larger than it is.
Yeah, and the probabilities of all these things happening so that Earth would be just the way it is, you know, I think we can quote, thank our lucky stars and planets.
Yeah, definitely. During the video, there were a lot of thank you, Saturns. Thank you, Saturn, for pulling Jupiter back. We appreciate it. All right. And Luke was wondering, could we artificially create a planet in the asteroid belt by colliding asteroids together?
I don't think that would be possible. For one thing, if you took all the those material in the asteroid belt and put it together, it would not, I think it would be like 1/10 of the size of the planet Mars. You know, all of that material had been thrown out, and most of it, and what's left, is not really very much. And they're few and far between. They make it look sometimes like the asteroid belt is just chock full of asteroids and other objects, but no, they're far apart.
Yeah, that's what I learned too. I didn't know, because from like space movies, you think of like asteroids constantly colliding like right next to each other. But apparently, if you stand on an asteroid in the asteroid belt, you wouldn't see any other asteroids around you.
Yeah, that's right.
Like blank space. Yeah. All right. We have a question from Izzy asking, why isn't there a lot of water on other planets?
I think, well, on the outer planets, there are in the form of ice. On the inner planets, Mercury is way too hot. Venus is also, there may be water vapor, a lot of water vapor on Venus, but there's no way at the high temperatures on Venus that it would ever condense. So I think the surface temperature of Venus would melt lead. So it's not friendly to liquid water.
Yeah. And Renee was wondering, why did Earth take most of the water from Jupiter and Saturn moving outward? Why didn't Mars or Venus, for instance, take it? Was it just kind of chance?
Good question. Mars, I know, is because it's smaller. And the core of the Earth forms the magnetic fields around the Earth, and that forms a barrier to the cosmic rays from the sun, the solar wind, and that protected the atmosphere of the Earth, you know, from being blown away. Mars was smaller. It didn't have as large a core to generate a magnetic field, and so the solar wind blew away most of the atmosphere and the water vapor that was in the atmosphere. And what was left was not very much water.
Yeah. And Atlas was wondering, could you go over again why there are no super Earths in our solar system?
Oh, yeah. They didn't make that too clear in the video. It was because as Jupiter moved in and it started flinging around all these materials that were forming the inner planets, a lot of those asteroids and planetesimals crashed into the super Earths and knocked them out of their orbits. And the stability of the orbits of the planets is very, very important. If you throw one out by just a little boost where it could wind up, and they believe that the being thrown out of their orbits, the super Earths wound up spiraling into the sun.
Okay, so basically they were just flung outward.
Yeah.
All right. How many planets would there be if Jupiter did not migrate? That's a good question.
Nobody really knows.
Yeah.
One of the things about those simulations that they run is that they get the results of thousands of simulations, and the results are expressed as probabilities. So those probabilities fall into complex patterns. And so when they look at the patterns, they might see that, oh, well, there's 25% chance that super Earths should have formed in our solar system. And maybe there's a 40% chance that Jupiter should have formed where it did, and a 10% chance of Earth forming where it did. But they don't have any answers to this. There's no way that they can get an accurate enough idea of the beginning of our solar system, how it was configured, and how the forces act over billions of years to figure out where we are today.
All right. Okay, Izzy was wondering if a planet runs into an asteroid, can it make the planet bigger?
Oh, yeah. Yeah. And all you have to do is look at the planet Earth, how our moon formed. Was back about 4.5 billion years ago. They believed that a large planetesimal planetoid about the size of Mars crashed into Earth, and it made the Earth larger, and the debris from the planet was known as called Theia. The debris from that collision threw debris around the Earth that later coalesced to form the planet Earth. So there's lots of material that can help form a planet like that.
Yeah. All right. And Janet and Steve were wondering, did this have an effect on the Venus and Uranus rotation direction? I'm assuming that's like the whole like the Tack hypothesis. Did it have an effect on changing the rotation?
Yeah, I know. Uranus rotates in the opposite direction of the other planets, I believe, and some planet on maybe even a 90-degree angle towards the sun. I'm not sure.
Yeah, it's kind of like tilted.
Yeah. That could definitely have been caused by the migration of the Saturn and Jupiter, and also by of collisions with other planetesimals or planetoids as it was forming.
All right. We have a couple of questions about how did ice form in space?
Yeah, it's so cold. Just the molecules that are out there, to be a liquid like water requires the ability to not crystallize. And the molecular structure of water crystallizes at 32 degrees Fahrenheit. So once you pass the ice line and you get out there, water will crystallize into a locked pattern of molecules. And not only water, but as you get farther out, you have all these other molecules that will start crystallizing from a gas form to an ice form. So you have methane, which is basically a gas, will form ice.
All right. Okay, so we have a lot of hypotheticals about the sun. So those we might save because we're not sure on a lot of these. Like if the sun becomes a black hole, we're not sure what would happen there. But we did have a question that I find interesting. Izzy was wondering, does the sun move like the planets?
Yes. It depends on how you think on how it moves. Mm-hmm. Like one of the ways that they discovered that there's exoplanets is by the wobble of the star. And it's because those planets orbiting the star exert a force on the star. And not only does the planet orbit around the star, but the star ever so slightly wobbles and orbits around that planet. Not very much in most cases, but enough that they can detect with telescopes. So that's one way that the sun can, or a star can move. Another way is that our sun is rotating in a spiral of the Milky Way galaxy around the center of the Milky Way, and it takes about 250 million years to orbit, do a complete revolution of the Milky Way for our sun. So if our sun is 4.5 billion years old, what is that? That's about 14 times around the sun, mm-hmm. or around the middle of the Milky Way.
Milky Way. Yeah. So the sun isn't just one point in space; it's also moving, and the planets are moving around it.
Right, and then the Milky Way is moving as well.
Yeah, exactly. Yeah, there's just a lot of movement happening. I know it feels which is hard to imagine because, like, when you're sitting, in front of your computer or screen, like, you don't feel like you're moving very fast. But yeah, we're moving through space and everything like that. All right. Okay, so I'm going to share my final screen. We are unfortunately out of time, but I did want to say thank you so much, Ron, for talking with us today. I had a lot of fun and learned a lot about Jupiter and how influential it was in shaping our solar system. So,
my pleasure.
Yeah, so thank you. And thank you all for tuning in. Thank you to our sponsor, the North Carolina Space Grant, and our members of the museum who help make events like Astronomy Days happen. If you'd like to join our members of the museum, you can go to that link at the bottom of this slide here. It's naturalsciences.org/membership. You'll save 10% on the t-shirt and the hoodie that are shown here, and you get exclusive access to members only events and other discounts as well. There are other great programs scheduled for this week. So we posted we'll post a link to our schedule with how to register for those in the chat. And we would love to hear your feedback on the program to help us improve. So if you'd fill out our survey at the link that we'll post as well. And if you registered for this program, we'll also email that survey link out. And finally, the recording of this program is going to be posted on the Astronomy Days program page. And also, I think Nancy linked to our YouTube playlist that it'll be posted on as well if you wanted to go back and learn about how cool Jupiter is again. Thank you again so much for attending, and we hope you all have a great rest of your day.
Bye.